Okay, here we go. Good morning. Good to see you all. Hope you all are doing well. Thank you all for checking in early and being ready to go. Hope you're having a great week. Let's get started. Here we are today, Tuesday, the 21st. Today, we're going to get into the first half of control charts. We're going to spend 2 sessions on overview and theory of control charts, and we'll spend 2 sessions on practical work with those control charts. Control charts, I think, are very exciting. I think they're very useful. They can be a little tedious, but it's important to get the details right so that they can do what they're supposed to do. So that's what we're going to do today. Tomorrow night, this is purely optional. I am doing a thing for the YCP Excel series. The title of my presentation and discussion is Leadership Through Crisis. That'll be at 7 p.m. tomorrow night. That's on Zoom. You should have an email from YCP Activities on the information for that in terms of the login and things like that. I just want to say that's purely optional. So if you're like, hey, I have no interest in hearing you one more time this week, that's fine. I love you anyway. If you do want to punch into it, and you can't, and you don't have the info or whatever, just hit me up on email and I'll get that to you. Or you can check your email for YCP Activities. I do think that it will be recorded. And so if you have something else going on, another class, stuff you got to do, that kind of thing, but you still want to see it, then just let me know and I'll make sure that you get the details for the recording. Looking ahead to Thursday, we're going to do some We Drive. So I'm going to put a problem up on the screen that'll jump off of what we cover today, and we'll work through it together. So I have one ready to go. I'll post that after we get done today, so you kind of get a preview of what Thursday is going to be like. But then I have some other ones that I haven't finished, and I probably won't have done before Thursday, and that's fine because we'll just roll into it like we would normally a U drive, except we'll do it as a group. Looking ahead to Sunday, 2 big things that are due. I say big because we haven't had anything due. Well, we have had the Way of the Warrior project due. We have homework 3 Alpha. That's on Pearson on my ops lab. That's due on Sunday at 1 minute before midnight. And then we also have the MRP Super B exercise that I posted on Canvas assignments the other day. So both of those are not going to take an extremely long time. But as always, I wouldn't recommend waiting until 11 o'clock on Sunday night to get started on it, because you might have questions, you might have areas you get hung up on. And it's not that I won't be available at 11 o'clock on Sunday night. It's just that you may not want to put yourself in that position. So those things are due on Sunday. And then a week from today, we'll go into the second half of control charts. 9 days from today, we'll do a We Drive on PNC charts. And then 1 week from Sunday, we'll have 2 more homeworks due on Pearson. That's 3 Bravo and that's 3 Charlie. And those are on X and R charts and PNC charts. So after we do our session today, you if you wanted to, in theory, you should be able to get started on homework 3 Bravo, but you certainly don't have to. So that's what our map check looks like through the end of next week. I'll just take a pause here and see if you all have any questions on anything I've talked about so far. Okay, with that, we'll go ahead and get started on control charts. So let me go ahead and get my pen fired up here. Do this. Okay, so I'm going to draw for a little bit, and then we'll eventually go to Excel. There's a couple of Excel documents that I put on Canvas, and I sent you a notification that they're there. And there's also a couple of tools that you'll need on Canvas. And just as a side note, so at this point, I'm looking at a sea of black screens, which I never really like doing. I always like seeing you. So if you'd please just unmute your video, I would certainly appreciate it. Okay, so let's talk about statistical process control. Okay, first let's talk about this word statistical. Okay, and that is the idea that we are going to attempt to control a process through the use of probability and statistics. That's really all that means. Okay, we have a process that's usually connected to some sort of production where we have output. And we'll talk some more about some examples of that in a second. And because we have output, we have performance connected to that. And we want our performance to be within a certain interval, within a certain segment of the performance that we desire. So we want to control that performance so that we have the kind of production that we want. This might mean quality. This might mean, something else, excellence, these types of things. So, for example, some common examples of production might be we are producing boxes. And so we want our boxes to be a certain shape, a certain weight, um, a certain percentage of fill. That's kind of a boring example. Or we might be on a sports team of any type, and we might want a certain performance there. We want a certain batting average. We want a certain miles per hour of speed when we throw a ball. We want a certain amount of rebounds per game. We want a certain amount of points scored, all those kind of things. So all those things I just described, we could view as production. We could also view as performance. Essentially, in my mind, they're the same thing. And we want that box to be a certain weight and a certain thickness so that it performs a certain way. We want to score a certain amount of points so that we perform a certain way. Ideally, we have a winning season. We want to throw the ball a certain miles per hour so that we have a winning season and those kind of things. So that's really the big purpose, is we want to control performance and we want to identify when performance is out of control. So I'll just put that on here as well. Out of control performance. And so the purpose of that is so that we can find out what's going wrong and fix it so that we can get back into the range or the band of performance that we want to be in. So let's just talk some theory a little bit deeper, but not too deep. And so to hang with this, you've got to reflect back on QBA 260, which is probably a year ago, I would think, for all of you, which is fine. But we might need to brush off a little bit of dust and then learn some new things along the way, which is cool. So the first thing is that any kind of process, we can assume that regardless of how the process behaves, if we sample the process, it will follow our old friend, I call this the hack daddy, the normal distribution. And we know that in the normal distribution, we might have either a population mean here in the middle, or we might have a population proportion. We'll just stick to a mean for now. And we have one standard deviation to the left or right. This covers about 68% of the values of the entire distribution from here to here. And One more standard deviation covers about 95%. Okay, so this is one standard deviation sigma. This is two standard deviation sigma, and the same on this side, except in this direction. Too much blue on the board. And then finally, we have the third standard deviation out here. And from here to here is just over, uh, let's see, 99%. It's actually 99.8%. Okay, so what? Why do we care about this? Well, let's talk about a practical example. And let's just suppose that Santa Claus came early this year and waves his hands, and we can all go back to the life that we were living before COVID. Big happy face. And so, to the baseball players out there, they get to go back to immediately they get a 2-week spring or training camp before they go back into the season. And so we want to see how the pitchers are throwing. And I don't know how fast we want the pitchers to throw, but there's a difference between how fast we want them to throw and what's feasible. So I'm just going to say that ideally we would want them to throw on average a 90-mile-an-hour fastball. Okay. Now, we also know that every time a pitcher throws a fastball or over the fastballs, they're not always going to be 90. Some might be greater. They might throw a fastball that's out here that's greater than 90. This is probably, I don't know, it depends on the deviation, but let's say this could be 95. We know sometimes a pitcher is going to step up and have a really super fastball. It might be way out here. It might be 102 or something like that. And then sometimes the pitcher's just something's going to be off in his technique or her technique, or not paying attention or something like that, and might throw, a fastball that's slower than 90, maybe 85, maybe as slow as 75. Okay. So, okay. Again, so what? Why do we care? Well, the question is how, what do we want to live with? Okay. And what don't we want to live with? And let's just say that we say from here and here and this range from the mean to the left and this range from the mean to the right, we would want to be symmetrical because this entire distribution is symmetrical. So let's say, hey, we can live with a pitcher that throws between an 80 to 100-mile fastball. We like that. If they're throwing down here, that's probably not going to win games. People are going to hit those balls. We're going to get more opposing base hits and all those kind of things. And that's not something that we want. And if a pitcher's throwing out here, that's great, I guess. But the question is, how long can he or she sustain that? And are they doing steroids? I mean, this is just kind of bizarre. I mean, we'll take it for now, but again, the question is, can they do that tomorrow? Can they do that next week? Are they going to throw their arm out? So within this range, 80 to 100, that's how we want to control the process. Now, the problem with this distribution as it is that I can't see. So let's say we have a pitcher and a pitcher throws here today and here tomorrow, here the next day, here next week, and so on and so forth. I can't tell after a while, I can't tell which day was which day. And so I can't really control the process. So what I'm going to do in control chart theory is I'm going to take this whole distribution, okay, and I'm going to tip it 90 degrees. So I want you to just watch. This is my upper control limit, and this is my lower. Okay, so when I say upper control limit, I have a value that's greater, 102. And when I say lower, or 100, and when I say lower, it's 80. So I'm going to tip this whole thing 90 degrees to the left, and I'm going to do some more things to it, and that's going to help me control the process over time. So I'm just going to wipe this whole thing, and I'm going to draw that distribution on its side. Okay. And this axis here is going to be time. And this is going to be, in this case, miles per hour of the pitcher. And remember, my mean performance, my desired, we'll say, was 90. And I certainly would like a 100-mile-an-hour fastball. So I'm going to put that here as my upper limit. I'm just going to put upper control limit for now. And down here, I decided that if that pitcher is throwing less than an 80-mile-an-hour fastball consistently, that is not a good thing, and we're probably going to lose games. So the way that I would proceed with this is, and I know some of you out there are cringing because you probably wouldn't really do this, but let's just say that these are weeks. I probably would do something like this. I think this could be sustainable. And over the course of that first week, I took an average of that pitcher's fastball speeds. And that average was 90. Okay, cool. And let's say that the second week, I took the average, and that average was 85. Okay. And the third week, the average was 87. And the fourth week, the average was 82. And the fifth week, let's say the average was 80. Okay. So thus far, I have a process that's in control, meaning I set these control limits. And because the pitcher's performance, their average performance, is inside the control limits, then I deem the process is in control. Whatever the pitcher, whatever the coaching staff, all these things, whatever they're doing the right things. Now, do I have variation here? Yeah. I mean, ideally, I would always want the pitcher to throw on this dotted line. But we know that isn't reality. Some days they have good days, some days they have bad days, some days they're in the zone, some days they're not. So I'm going to have some deviation, and that's fine. This is what is called normal deviation or normal variation. Okay. Meaning that we're just going to have some fluctuation here. All right. But because I've set these control limits where I had, the process is still in control. Now, let's suppose that I continue measuring. And the same process, okay, I keep taking the average for the week. And of course, with all this, I'm taking a certain amount of measurements, which we need to remember. That's our old friend from statistics, N. So let's say I have the pitcher throw 5 times, once every day during that week, and I take the average of those 5 times, then my N would be 5. Okay. My N is not the number of times that I measure it. My N is the number of measurements. Okay. And we'll talk more about that. All right. So each time, 5 times throughout the week, I measure it, I average it, that's what I get, and so on and so forth. Now, let's say that I continue doing this, and that 6th week, the pitcher's throwing an average of 75. And the 7th week, an average of 74. And that 3rd or that 8th week, an average of 72. Okay. At this point, and for the scope of this class, we're going to call 3 points outside of the control limit. If we have that consecutively like this, we are going to call that out of control. All right. So something is happening here where something's going wrong. Maybe the pitcher has an injury. Maybe the pitcher is trying something new and I'm not aware of it. Maybe my pitching machine is broken and it's registering pitching times that are slower than what the pitcher is actually pitching. Okay. And so all of this is what is called, it's not the best name in the world. And if I was king for a day, I would rename it. But this is called assignable variation. Okay. And what does the word assignable means? Well, that means that we should seek to assign this variation to something that is causing it and fix whatever that is, get rid of it. So if the pitching machine is broken, I should measure the pitching machine on someone else, validate that it's broken, and get a new pitching machine and see how that affects performance. If the pitcher is trying something new, I probably want the pitcher to go back to what he or she was doing here so they can get back in control. Okay. And later on, once we're done with control charts, we'll go through the next step, which is if where we have this something like this going on, how we can approach that and kind of dissect our approach. And that's actually called a fishbone diagram. Some of you who have had total quality management and other supply chain classes have probably seen the fishbone diagram. For the rest of you, I think it's a neat tool that goes hand in hand with this. So, but for the purpose of our overview discussion right now, it's what I want you to walk away with is that what we're doing, and the central limit theorem allows us to do this, is to take that normal distribution and turn it on its side. Okay. And then we can come up with our own control limits. I'm going to talk about how we do that here in a second. Once we do that, we start developing our control chart. And then we're going to take the average performance of whatever it is we're measuring. In this case, it was a pitcher. All right. These are not individual pitches. These are averages. And we're going to plot them on this diagram and see how performance is going. And then once we get something like this, we could have it down here. We could have it up here. We're going to deem that as out of control. And in the real world, we probably want to stop production. We probably want to tell that pitcher, hey, stop. Whatever it is you're doing, stop. Let's take a look at this so that we can get you back in between these two. Okay. And again, we might have a pitcher throwing up here well above 100 miles an hour. I like to view this as that isn't necessarily wrong. It's just kind of interesting and a little bit abnormal. Then we would still want to know, hey, what are you doing, dude? How did you get from here way up here? Is it some kind of protein you're drinking, or did you change something up in your personal routine? And then, like I said, if they're doing something that is not sustainable, then when is that crash going to come back? If they're throwing like this up to the playoffs, can they throw that way in the playoffs? Can we count on them to throw that way? What we don't want is to have this kind of performance and then we crash and go way down here. Okay. Cause then we'll really have lost games. So even when we have something like this, for the purpose of this class, we'd still say it was out of control. We'd investigate it a different way, but probably not entirely. We still use the fishbone diagram to do that. Okay, so, and then one more thing that I'm going to talk about much more is throughout all this, we have our old friend from statistics, sample size. And that means that for every sample, okay, this right here is a sample, we took 5 measurements and we took that average. For here, we took 5 measurements. For here, we took 5 measurements. Now, we have, in this case, 8 samples. All right, so I'm just going to write it here. It's not the only time I'll write this, but this is a common mistake that warriors make, is that they confuse sample size with the number of samples. So sample size does not equal the number of samples. Okay. And this, if this doesn't resonate with you, I just recommend that you park that somewhere and keep asking yourself, why don't I get this? What does this mean? Again, in a sample, I have a number of measurements, in this case 5, but that's one sample. I might have more than one samples. In QBA, I know this now that I've taught QBA going on my 2nd semester, we often deal with one sample. In this course, when we talk about control charts, we're going to talk about more than one sample. So there's a little bit of difference there, but if you get this here, park it somewhere in your notebook, tattoo it on your forearm, do all the above, then you'll get this, you'll keep these 2 things straight. Okay. And in the formulas we work in, you're going to need to know N. Okay. Which can kind of mess you up. You can see here, if you confuse the 2 and thought that N was 8, well, because N is really 5, the numerical value that you get is going to be off, and that's going to throw everything off. Okay. So let's see. One more thing I want to talk about very briefly, which is, okay, how do we establish control limits? Well, let's go back to this. All right. Remember, in QBA, you did what's called a confidence interval. And you did this, and this may or may not come back to you, and in either way, that's okay. But a confidence interval is an estimate on what either the population mean or the proportion is. We are not doing confidence intervals. We're establishing control limits. So they're not the same thing. Okay. But there's some relationship in the formula. Okay. So let's just talk about it. Now, remember, ideally, we would always want to get the mean. Okay. In our example with the baseball player, we would always want that baseball player to throw 90 miles an hour every time. That would be awesome if we could get that. But we know that that's not so much feasible. Sometimes they're going to throw faster. Sometimes they're going to throw slower. It's just a question of how slow are we willing to live with, and how fast do they get before we kind of start shaking our head and looking like the RCA dog and tipping our head to the side. So remember, with confidence intervals, we would say things like, okay, we want to capture 90% of the values around this one. Okay. And so we would say, okay, how do we do that? All right. And let's take an example where we want to capture we want to capture 95% of the values around the mean. That doesn't have to be 95%. You could say, hey, I don't want very much variation at all. So I only want an interval of 10% around the mean. That would be a super, super tight control limit. But it all depends on what you want. And here we're going to deal with higher values. Okay, so 95%, 99%, those kind of things. So how do you figure out what this value would be and what this value would be? Well, first thing you've got to do is realize that if this white area here in the middle is 95%, that these shaded areas combined are going to be 5%. And I apologize for my kind of, not the greatest drawing in the world, but if blue plus blue is 5%, then this area over here is 2.5%, and this area over here is 2.5%. Okay. Okay. So what? Well, this hopefully will come back to you from statistics. What we need to do is turn all of these values into decimals. So we're just going to do that real quick. That is 0.05. That is 0.025. This is 0.025. And this is 0.95. Actually, 9.9500 is the way that the Z table likes to see it. And when I say the Z table, I put a Z table on your Canvas today. You probably want to print one out, or at least have, so you can refer to it. So the question is, what Z score, all right, would this be? Would this value correspond to? So we're trying to find out Z. And whenever we're trying to find out Z, if we have a probability, we can figure out Z. Well, one of the ways we can figure out Z, if we go into the table and we look for this, we're actually going to find the Z score that equates to this over here. So we can do that. We can go into the Z table, and I like to refer to it as shrinking down and getting inside here and looking for, we're going to go first on the negative side of the Z table. Actually, I can do that here on my screen. All right, so this is our negative side of the Z table, and I'm looking for 0.025. So I'm going to go down here. Let me shrink. Let me get this bigger. Okay, so there it is right there above my cursor. Okay, 0.0250. And so that's a probability, but to get a Z score, I have to go to the left and above. So the Z score I would need is negative 1.96. Okay. And really, in the formulas that we're going to be working, you only need a positive Z score. So we could do the same thing on the other side of the distribution. We would have to do a 1 minus. So all right. So if you remember, so the point again here is, what is the Z score that we're going to need? So if we go over here to the right-hand side of the distribution, well, there's two ways we can do this. One way, if we know the Z score for this side is negative 1.6, that refers to that probability, because this thing is symmetrical, the Z score for the right-hand side is going to be 1.96. So we don't even really need to look it up. But if we really, really wanted to look it up, we would start with that probability, 0.025. We would take 1 minus 0.025, and that would give us 0.97, whatever that 9975. Okay, 1 minus 0.025 is 9975. I think I've got that right. Let's see. And 0.9975. I think I've got that messed up. It'd be point. It wouldn't be that. Regardless, I just know that this is. I'm trying to think of why I messed it up. But anyway, the z-score I would use is 1.96. This is probably a lot more complicated than it needs to be. The bottom line is if we want a 95% control limit, in that case, we're going to use a z-score of 1.96 in our formula. So at this point, you're probably going, okay, great. What's the formula? And that's what we will do. So all right, before we go into that, just real quick, here's where we are today. We have 4 types of control charts. We have an X-bar chart, which helps us measure the mean performance. We have a R-bar chart or an R chart, which helps us measure the dispersion. So what an X-bar chart does is, let's say we have the mean. Let's go back to our picture. An X-bar chart helps us pick up on, let's say this was the average performance. And again, we would want the pitcher to perform on average, assuming that average is good. But the X-bar chart will help us pick up. Remember how the pitcher was below the lower control limit? Will help us pick up and see if the mean has actually changed. And the new curve is something like this. Okay, maybe the pitcher's actually pitching around 72 miles on average and then much lower than that and sometimes higher. But that'll help us. This is what an X-bar chart will help us pick up on. An R-bar chart is the variation that's occurring. So here, we might have the same average performance from the pitcher, and we didn't do this yet, but it might be that the pitcher is performing a lot less consistently. So some days the pitcher's just throwing out of his or her mind and some crazy fast pitches, and other days just like, what the heck? Where did that come from? That's what an R chart helps us detect. Okay. We have other types of control charts we're not going to get into today, but we will get into a week from today. That's our P chart, which stands for percentage or proportion. Again, proportion is a statistical term that might come back to memory. And then we also have a C chart, which is another version of an error chart. Okay. So let's get rid of these real quick. Okay, so as we look ahead just slightly, let's talk about a few more things. These up here have to do with numerical variables. Okay, so things like speed. And these are continuous. And oh, by the way, I have a picture of this finished on a Canvas page that's above the one for today. It's accessible to you. But it's helpful to walk through this while we're here. So these are continuous. So speed, 82 miles an hour. I don't have to end on a whole number. I could keep going to the right as far as I want to go, as far as my pitching machine could measure. That's just one example of a continuous numerical variable. Weight is another one. Arguably, income is one. If I wanted to measure down to the fraction of a penny how much a person made. Time, that's kind of like speed. So these are all examples of continuous numerical. And when I have that kind of variable in a problem, that's usually an indicator that I'm up here in terms of I want to do an X and an R chart. Now these go hand, if you do one, you want to do the other one, because you want to both not just understand how the mean the tendency might have shifted, but also the variation that's involved. Okay. Now down here, these are discrete. And we usually convert these into a proportion. So it might start out as something like 4, but then turn into point whatever 1, 2. Okay. And a common thing for these are like errors. So going back to our baseball analogy, obviously I don't want any errors in a game, but if I do have errors from players in a game, I want to control the amount of errors. Or if I'm in production, let's say I'm making tables, I'm going to make faulty tables. Not purposely, but it's going to happen. I want to minimize those types of errors. So if I have a problem that looks like that, I'm going to be down here with these charts. Okay, so that's an overview. So the first thing, and that's what we as warriors work on, is we see a problem, we think about, okay, which landscape are we in? Are we up here with this type of situation, or are we up here? And to do that, we've got to really read the problem and understand what we're trying to do. Let's assume that we're up here, and so we've made this decision that we're up here. Okay, the next decision we need to, or next question we need to ask is, do we know what's called sigma, or the process standard deviation? Okay, now you may remember this from statistics. We have the central limit theorem. And so what we're doing here is sampling. When we sample, we usually know something about the population mean that we're looking at. And the central limit theorem tells us that we can assume that the sample mean, which is what X bar is, will equal the mean for the population. Okay. There's more theory behind that, but that's how that works out. But the other thing about this, if we know sigma, then we're going to use a certain type of formula to determine that X bar chart. So this is yes or no. If it's yes, we're going to use one formula. I'm going to show you that here in a second. If it's no, we're going to use a different approach. And I'll show you that in a second. All right. So I like to call this question down here, meaning, am I here or here? This is the $1 million question. What am I talking about? Am I talking about continuous numerical variables, speed, weight, income, etc.? Or am I talking about something that's discrete? If I'm up here, okay, I answered my $1 million question. My $500,000 question is this one right here. Do I know the standard deviation for the population or process? And in this context, those are essentially synonymous. Okay. If I know that standard deviation, then I'm going to use a certain formula. If I don't, then I will use a different formula. And you may ask yourself, well, how do I know that? How am I going to be able to tell that? Well, read the problem. If the problem tells you that the population or the process standard deviation is a certain value, then that's what that is. If there's no mention of what sigma is, then you want to use a different set of formulas. Okay, so let's go ahead and work a problem. So I'm going to get out of all this. And if you have it, you want to pull up this right here. This is our X chart only, sigma known, sterile. Okay. So to start out with, here's what I have. In this example, we are producing boxes. Nice, boring example. And we have, what we're doing is we're taking 9 boxes every hour. So the production line is kicking off boxes off the assembly line, probably much more than 9. But we're taking 9 just at random and putting them to the side every hour. And then somehow in that hour, somebody, maybe Ellie, is grabbing them and measuring them and getting an average of those 9. Okay, so Ellie does this for the first hour, she gets 16.1. She does it for the second hour, she gets 16.8, and so on and so forth. She does it for 12 hours, her entire shift. And what we're trying to do is see, is the box production process in control? All right, so here's our givens. We want to be in control 97% or 97.5% of the time. Okay, we're willing to accept that the other part of the time we're not. Okay, so actually this would be 95% of the time. So, all right, a 95% would give us the 2 tails. So the right-hand tail, if we go to our Z table, or another way we can do this, probably a simpler way, is to use the norm S dist function. Okay. Of course, I don't know what Z is yet. So I think it's my inverse function. Let me get bigger here. Not big enough. All right. Okay, so this asks me for a probability. So if I say 0.95, it's going to give me a Z-score of 1.65. Of course, that's not really what I want. I'm just going to go ahead and give you the Z for now so we can keep on moving. Okay, so we're going to use a Z-score of 1.96. Okay, so I have these givens up here. 95% means I want to be 95% in control. I want to have limits to the left and right within a 95% symmetrical interval around the mean. I have Z as 1.96, I have N as 9, and sigma as 1. So the first thing I'm going to want to do here is get what I call the average of the averages. And I'm just going to park that down here, and you'll see why in a second. So I'm going to call this X double bar. Okay, and the reason it's not X bar is because all these are their own individual X bars. And when I take the average of all of them, I get the average of the averages X double bar. And I'm just going to do that the same way I've always done it, which I'm going to take the average of all these. Okay, and that's 16. All right. And probably the next thing I want to go ahead and do is graph these. So I can highlight either both or just one column. Either way, if I use this function, I go to insert and I use what I call my connected scatter plot. Even though this isn't a scatter plot, I'm going to use this one right here. And it gives me this nice, pretty little thing. Now, cosmetically and analytically, we remember from statistics that I can truncate meaning shorten this y-axis. I don't have to have it go down to 0. And to see the nature of this variation, I'm just going to cut it. There's no hard and fast rule, but I'm going to cut it at 12. So I'm going to go in here and format this axis. And over here, I'm going to make that 0 into 12. See how I can see that variation more? Okay. And I don't really know what I'm looking for yet, but this is going to help me find it when I do. All right. And then just, okay, so I'm going to continue to add on to this chart here. And the formula I'm going to use right now, because I know my process standard deviation, again, that's that $500,000 question. The formula I'm going to use is, I'm just going to write it up here on the screen. Okay. So I'm going to have a control. What I'm trying to do now is establish the control limits. All right. This is going to look very familiar if you remember your confidence interval formula from QBA. So I always start with the centerpiece. And in this case, I'm doing an X chart. Okay. This right here is about to become an X chart. Okay. And remember, my standard deviation or my normal distribution is going to be over here. Okay. But you don't need to draw all this. I'm just showing the concept. I'm going to put an upper control limit up here somewhere. I'm going to put a lower control limit down here. To establish what those control limits are, I'm going to use this formula. X double bar plus or minus. Okay. That plus is going to give me the upper. The minus is going to give me the lower. Z times sigma over the square root of n. This dude right here is known as the sampling standard deviation. Okay. And that's our X double bar. We have Z because I gave it to us at 1.96. I'll get better on explaining how to determine what Z is. I'm just not on my game there today. All right. So what we want to do is, what I'm going to do over here is I'm going to make a place for upper and lower. That's just the way I like to frame it. Okay. But you probably want to copy this formula down somewhere because it's about to disappear. All right. So I'm just going to put upper and lower. And I could say upper control limit. I could say lower control limit. It doesn't really matter. What I like to do, you remember everything from Z on in our formula. I already have my X double bar, as I like to call it Z delt. Just, I don't know, because it's Z and it has the delta of the difference. And so I'm going to grab my stuff I need to compute that. I'm going to grab that Z. I got to remember my PEMDAS. I got a bunch of stuff going on, so I'm definitely going to need some parentheses. I've got sigma in the numerator, and I'm going to have the square root of n in the denominator. And I got to make sure my PEMDAS is tight. And I think it is. And that is correct right there. So remember, I'm going to add to it to get the upper. So I'm going to take that X double bar and add Z delt to it to get my upper. And then conversely, to get my lower, I'm going to subtract my Z delt from my X double bar. So I'm going to refer to that X double bar, and I'm going to subtract my Z delt. So I have an upper and I have a lower control limit. Now, you can do what you want to here, but in terms of colors and all that. Let's just say that for upper control limit, I'm going to put a green. So I'm going to go here. Yep. I'm going to grab a line. And that line 16.65. It doesn't have to be perfect. I'm just going to draw that line right there. I don't want to do that. I'll make it green. And I'm going to crank its width up a bit so I can see it. That's my upper control limit. I'm going to move it around in a second. And then I want a lower control limit. It's like watching paint dry, I know. Come on. There we go. And that is 15.34. So I'm going to put that about there. And I'm going to turn it to be red. Okay, cool. And there's a couple more things I want to do here. I need a line that reflects X double bar. And X double bar is right at 16. So I'm going to put that right there. And I'll make this one black and dotted line. If you want to copy this format that I'm using right now, I'd say that would help me out, but I'd know what I'm looking at. But you don't have to. You could use purple. It doesn't really matter. As long as I can tell that you've identified an upper control limit, put it about the right place, a lower control limit. Now, we're not done yet. We need to see what points are out of control. So one way I like to do this, let's just start with the upper, 16.65. And just to make sure my graph is correct, I'm going to go down here and highlight every point that's outside of that. So that's outside of that. And I'm going to do it with a little shade of green. Okay. So 16.8 is higher than 16.65. Those are not. And that one is. So it looks like I have 2 points that are above the upper control limit, and that makes sense. So while I'm thinking about that, I'm going to get some circles going on. And you might be thinking, is there a faster way I can do all this? Not that I know of, but that doesn't mean that there isn't. So if you can figure out a faster way to get Excel to do this for you, then more power to you. But, or you could draw it by hand. It doesn't really matter to me. I'm doing it by Excel today and a little bit by hand. So I have 2 points that are above the upper control limit. Does that mean alone that the process is out of control? No, it doesn't. Not by our standard of being out of control. If I had 3 consecutive, either above or below the control limit, then it would be out of control, but I don't, so it isn't. Let's look at that lower control limit though, because I got this here and I got that there and I got this here. So let's see. Well, I'm looking at 15.34. So there's that one. 15.2 is lower than 15.34. So I'm just going to give it a little shade of red and keep on going. And oh, look at all this mess. That's out of control and that's out of control. Okay. So where's this one on day 7? That's that dude right there. Boom. And then these other dudes over here. Okay, now you might be going, well, these two are consecutive below, and then that one is above. I will make a question or questions for you much more straightforward. But just from a general knowledge point of view, I would say at this point from day 10 on, this process is out of control because 2 days, actually, we skipped, no, that's the 13th. Yeah, 10, 11, and 12. So 3 consecutive days, we had averages outside of the control limits. So something is going on that shouldn't be. Maybe a machine is broken. Maybe Ellie's scale is faulty. Maybe Ellie is weighing the boxes probably incorrectly. I doubt it. Maybe we have a new worker on the assembly line who came in on day 9 and we rushed them in there and didn't give them the proper training. And so they're not filling the boxes properly. There could be a number of things, but from day 10 on, I would say that our process is out of control. Now, I'm going to quickly go into the situation where sigma is not known. And quite frankly, I wouldn't get too hung up on the whole z-score thing, and you're going to see why. Regardless of the situation, whether we know sigma known or not, we have to use a certain chart to do our charts. We do a certain table. So this is going to make sense here in a second. Let me go to this. Let me get it bigger. Okay, so this is our second and final example of today. All right. And let's talk about some givens. So here, let's say we're still measuring boxes. Okay. But now we don't know the standard deviation for the process. So this would be an example maybe where we have a new process and we haven't had a process that's been running for a long time. So we don't know the process standard deviation. Okay, so we go through the same kind of thing. Let's suppose that these are box weights again, and let's make sure that we know what we're looking at. So this time we've got Teresa that's taken samples of these boxes. And each time Teresa does it, she uses a sample size of 9 boxes. I'm going to have to use a Z of 3, and I'll explain more why that here is in a second. When I don't know the process standard deviation, I essentially have to use a Z of 3. That's a 99.97% control limit. And again, I'll explain why that in a second. Let's talk some more about what we're looking at. So Teresa takes samples. She takes that average of the samples. So she weighs those 9 boxes. She takes the average weight. But what she also did was she took the minimum weight of the sample and the maximum weight of the sample. And the difference between those two is the range. All right. So that means that from the largest box, the heaviest box, and the lightest box, there was a difference of 6 pounds. Assuming these are pounds or ounces, it doesn't really matter. There was a difference of 6. For the second sample, the average of the sample was 12. The range was 4. Okay. And so on and so forth. So that is what we're looking at here. And she took 10 samples. Okay. Don't confuse the sample size with the number of samples. To get that 14, she had 9 values that she added up and then got the average for. Okay. So most of the time when you're looking at a narrative and you see something like this, I give you a data table, you really want to read the narrative to get that sample size. Don't go down here and look at this and go, oh, I have a sample size of 10, because that's not what's going on there. Okay. So one thing we could do first is we could plot these like we did before. connected scatter plot. And that's what that looks like. And just for now, I'm going to leave that like that. I could cut it down to 6 if I wanted to really show that. But this, as it is, really shows that it shows the variation. I don't know if I'm out of control or in control, but I'm going to find that out. I'm going to do my same thing before. I'm going to find X double bar. And again, I'm going to give myself some space because I'm just going to end up putting upper and lower down here. And that's just a technique that I use. And again, I'm going to take the average of those averages, right? Like this, 12.6. Okay, super. But since I don't know that process standard deviation, I have to use a new formula. And that formula I have to use is not this one. I have to use this one. So control limits, I'm still going to start off with X double bar. That's cool. I'm still going to have a plus or minus. That's cool too. But I'm going to use this formula A2 times R bar. Okay. So before I go to tell you how we get A2, first let's talk about how we get R bar. Okay. R bar is simply the average of the ranges. Okay. Notice it's not an R double bar because these aren't averages. These are actual ranges. So when I take the average of these, it's going to be the average range. So what I'm going to do, probably want to jot this formula down somewhere before we jump around a little bit. I'm going to go ahead and figure out what R bar is. I'm going to go over here and I'm going to figure out average. Boom. So my R bar is 5.2. And I'm eventually going to need upper and lower for R bar. So I'm just going to park that there. Okay. Now, what's the next question is, what is A2? Well, remember my sample size is 9. So you're going to have this chart. This is on your canvas for today. Factors for computing control chart limits with 3 sigma. Okay. So when I don't know the process standard deviation, I have to have a control chart limit of 3 sigma. Okay. That sigma 3 sigma is different than the unknown process standard deviation. I have to go down here and first, my number one question is, what is my sample size? If I have a sample size of 9, I'm going to just walk my way over here and get that mean factor A2, which is 0.337. Okay, so I'm going to put this aside. I'm going to remember that 0.337. If I wanted to just keep things kind of simple, I could go A2 times R, okay, and figure out what that is. I don't have to. And that's going to be that R bar down here. We'll grab that. And I'm going to multiply it by that A2 right there. And essentially that value there is kind of like Z delt. So I'm going to go over here and add that value to 12.6. And then I'm going to go down here and I'm going to take 12.6 and subtract that value. And that gives me my upper and lower. And then I'm going to put them in here just like I would. Let's see if I can do this quickly. So 14.35 is about right there. Let me ramp this up. like that shade of green, but you get the idea. And then I'm not going to do the colors right now because I want to get this R chart in before we run out of time for today. And 10.84 is my lower, so that's roughly there. Okay, and I'm going to go through my same process to see that everything's good to go. And this is my X chart. When I say good to go, that I can identify points out of control. Okay, so once again, up here, I'm looking for everything greater than 14.35. That's going to be those two. And then I'm going to do a second pass and look for everything that's lower than 10.84. That's going to be that. Ugh, too dark. That's going to be that. And that'll be it. Okay. So it's those 2 points out there out of control, these 2 points. So we have some variation, we have some assignable, but the process itself is not out of control according to this. We have 3 points up here. I must be missing one. This one. No. I don't know. It's in there somewhere. I want to get onto the R one though. Let's talk about R. There's only one way I can do R, and that is, it's actually a simple formula. So with R, I have separate formulas for the upper and the lower. So let's do UCL for R. So upper control limit for my R chart is going to be D4 times R bar. And my lower control limit for R is going to be D3 times R bar. All right. So this is the one time really in all of control chart theory where I don't have a thing where I have a plus or minus kind of thing going on. Okay. So you want to jot these down somewhere. And what we're going to do is we know D4, D3. Again, the key when I go to my chart is what's the sample size, which is 9. So where'd my chart go? Here it is. We'll go back over here. We'll go down to sample size of 9. I'm going to walk over to D4, 1.777, and lower is 0.223. So 1.777 and then 0.223. And for my R chart, now I'm going to move this and my lines aren't going to move because that's just the way it is. So I'm just going to put those up here. I'll fix that later. For my R chart, I need an entirely different chart because I'm looking at a different thing. So to plot that, I could just go like this. I don't even need those X values because it'll do the same thing anyway. And I want to put this down here. Okay.
I have a question.
Yes.
So earlier for the for the A2, we used the sample size 9 in the chart, but you just used 10 in the D4, D3 one.
Yeah, because I was going too fast. Good catch, though. I want to use 9 again. So that's
Okay.
my mistake. So this is going to be, let's see, can I do this without it disappearing? This would be 1.816, and that would be 0.184. Good to go? Yeah, good catch. I appreciate it. I was just going too fast, trying to get it in before we turn into pumpkins, or at least I do. Okay, so same here. It's just going to be 5.2 times that D4. And then here, it's going to be 5.2 times that lower. And so that 9.44 is really going to be off my chart. So if I was wanting to do this right, I would adjust my axis so that I can get that 9.4 in there. And my 0.95 is going to be way down here. Right about there. Say, so on our R chart, hopefully it's pretty obvious. I'm still going to put in what I call my centerpiece. So that 5.2, I would still want to line through it. But I'm sure it's obvious to all of you that my range, my process for range is in control. I don't have any points above the upper or below the lower. My process is also in control for mean or average, but I don't know. Things are getting kind of interesting here. In reality, would I stop the whole process to investigate these? No, but I would kind of want to keep my eye on things. Okay. Now, this situation where we don't know the process standard deviation, I guess it depends on the situation of how realistic that is. With new processes, I think that's very realistic. As far of a tactical perspective for this class, because I want you to do an R chart every time you do an X chart, I have to give you certain things to be able to do that. And because the only time I can do an R chart is with a 3 sigma and our handy dandy A2, D2, or handy dandy A2, D3, D4 table, I really, I can have you figure out Z values all day, but when it comes to doing that R chart, I have to give you a Z value of 3, which covers 99.87% of the values around that mean. Okay, so there's some tactics there where you could say, well, I'm going to assume risk on trying to figure out what Z is because he has to give me a certain thing. Anyway, so a lot covered there, especially in the last couple minutes. That covers how to do an X chart and an R chart, whether we know the process standard deviation or if we don't. I don't really like the way these look right now. For the better example, I like the other one that we did. Oh, no, this one right here. This to me is what right looks like once you're done. Not necessarily these specific colors, but I want to see clear how the process is occurring. So if you didn't change that axis, you just kind of have this one little line that's hard to see. I want to see your control limits, both that you've figured them out and also that you've depicted them on the chart and how they compare against the average and particularly where they're out of control. So I want you to circle them when they're out of control. You might ask, can I do all this by hand? I.e., can you draw it? Sure, as long as it looks the same way this would. Can I figure out a faster way to do this on Excel? Sure. And a matter of fact, if you do, let me know how you did it so I can teach other warriors like you how to do it in the future and they don't have to spend so much time cutting and pasting all these kind of things. Okay. Questions on anything? I apologize. We ran a little bit over. I owe you 5 minutes somewhere. Questions on anything, big or small, whether it has to do with this stuff or anything else. Okay, super. So Thursday, we'll begin with a tiny little bit of review and then we'll get into some problems. I may post some of them ahead of time so you kind of have a little bit of a preview. Regardless, I will see y'all on Thursday. Have a great week.